Welcome to solverfy.
This is the answer to chapter 27, problem number 40 from the Smith Organic Chemistry textbook. And in this problem, we're asked basically to work backwards and to look at each of these three products and determine from what starting materials we could make these products by making use of a thermal 4+2 cycloaddition, so a Diels-Alder reaction. And so probably the best way to do this is to start by looking at each of these and thinking, okay, so what bonds are probably breaking here, and thinking about how that would come about. So when we look at A, the bonds that are going to break are this bond and this bond. And then if we think, okay, so what would those bonds breaking look like? We can draw the movement of electrons, because remember, all of these reactions are at least theoretically reversible, all paracyclic reactions. And so that would look like this. So the electrons of that bond would move to there. The electrons of this double bond in the product would move to there. And the electrons of this bond would move that way. And so when we're looking at this, we see that we actually have an alkyne as one of our starting materials. And that's okay for a cycloaddition for Diels-Alder. That's perfectly fine to have an alkyne as a starting material. And so now that we know the bonds that are breaking in the way that electrons are moving, we can go ahead and start to fill in what our starting materials are going to look like. So we're going to have a backbone that looks like that, and then we will have a backbone that looks like this with the alkyne, the triple bond. And so let's put the C's in. Why not? So that's fairly straightforward. And then since we know that we have that in the alkyne, we can go ahead and fill in the rest of the alkyne. Going to be CO2, CH3, and CO2, CH3. So there's our alkyne for A. And then we do just need to consider what the stereochemistry is saying about this other starting material. And so remember, these thermal 4+2 cycloadditions are suprafacial. And so we're going to need to put the same stereochemistry on these two substituents over here. Oops. 1, 2, double bond, 1, 2. Yeah, right. Okay. So there we go, like that. And so that is going to be our answer for part A, because these two starting materials, when put together to do a 4+2 thermal cycloaddition, will give us the product that we were given for A. So then for B, we can go ahead and do the exact same thing. So we can look at what bonds are breaking and forming here. So the bonds that we're going to want to break are, again, bonds there and there. We can, just as we did for A, we can say, okay, so in order to make that happen, how are the electrons going to move? So just like this, in a paracyclic fashion. So now we see that unlike in A, where we had an alkyne and a diene, we're going to have a diene and an alkene. And so we can do exactly what we did again. We can start with at least the diene's backbone there, and then we can look at our alkene. And then we need to think about the stereochemistry on these various substituents. And so we see that the two CO2CH3 substituents are cis to one another. They have the same stereochemistry. And so since they're cis to one another in the product there, uh, we're going to make them cis to one another in the starting material as well. So CO2, CH3, CO2, CH3. Okay, and so that's the alkene piece of our, or the alkene reactant of the two reactants we're asked to draw. There is that piece. And then we just need to look at how the substituents on the diene are going to look. And so for A, they were cis to one another, but here in B, they are trans to one another. And so we need to account for that. So we can draw the top substituent exactly the same way that we did in A. It has the same stereochemistry. It's dashed. And then to get the trans ethyl group on the other side, to get the wedged ethyl group, we're just going to have to change the stereochemistry from how we had it in A. So for A, we had both of the double bonds had trans E chemistry. So we're just going to change them, or change this one at least, and make it Z. So it'll be cis. So there we go. That's how that will look. And when these two reactants are put together, we will get the product that we were asked to start from. So then for C, we're going to follow the exact same pattern that we followed for A and B. So there are the bonds that we want to break. Here is the movement of the electrons that we need to facilitate that. So again, we're going to end up with a diene and an alkene. So we can go ahead and draw at least the pieces that we know to get started. So diene, alkene. So now we see that the two CO2CH3 groups are trans to one another here. So in order to make them trans to one another in our product, we will go ahead, CO2CH3, and make them trans to one another in our starting material. So that's the alkene piece handled. And then for the other piece, we see that our two ethyl groups are once again trans to one another and wedged, or pardon me, and dashed. And so we can go ahead and draw them the same way that we have been. So there's one and there's two. So that matches how they were drawn in A and differs from how they were drawn in B. And of course, that makes sense because that is the stereochemistry at those positions correlates with different ways that we are drawing the starting materials. And so this problem is a good overview on how the stereochemistry at each possible position of the diene and the alkene or alkyne goes on to affect your stereochemistry in the product. And that is the answer to chapter 27, problem number 40.